Right now, without any effort on your part, your body is being pulled very gently downward. The mattress beneath you is pushing back, just enough, and somewhere in that quiet balance between falling and being caught, gravity is doing its slow, patient work. It has been pulling on you since before you were born. It will keep pulling on you all night, so steadily that you stopped noticing it decades ago. This is the same force, the exact same invisible tug, that in certain places in the universe becomes so concentrated, so folded in on itself, that it stops being gentle at all. Tonight, we're going to talk about those places. We're going to talk about black holes. You don't need to brace for that phrase. I know it can sound like the beginning of something frightening, the kind of topic that shows up in movies with sudden music and wide-eyed actors staring into swirling darkness. That's not what tonight is for. Tonight is for something much slower. We're going to take this idea apart the way you might take apart an old pocket watch on a quiet afternoon, laying each small piece on a cloth, looking at it in good light, understanding what it does before moving to the next one. No piece will be rushed. No piece will be skipped because it seemed too basic to mention. If something seems obvious to you already, let it wash over you like a familiar tune. And if something is new, there will be room to sit with it before we move on. This is also a good moment to give you permission for something. You are allowed to fall asleep during this. In fact, that's the actual goal. This isn't a lecture where the payoff comes at the end, and you need to stay alert to catch it. There is no ending you be tested on. The value of this hour isn't in reaching a final destination wide awake and triumphant. It's in the process itself, the slow accumulation of small, clear ideas, one settling into the next, like snow falling in windless air. If your eyes get heavy in the next 10 minutes, that's not a failure of attention. That's the whole design working exactly as intended. Wherever you drift off, you can pick up the thread another night, or simply let the rest become part of the background, the way a familiar bedtime story doesn't need to be finished to do its job. I also want to promise you something about how this is going to be explained, because black holes have a strange reputation. People talk about them as though they're one of the few genuinely incomprehensible things in nature, something so alien that ordinary human understanding just breaks down completely. That reputation isn't entirely fair. It's true that black holes push our intuitions in strange directions, and it's true that some of the mathematics involved took brilliant physicists years, sometimes generations, to work out fully. But the core ideas, the pieces that actually make a black hole make sense, are built from things you already understand. You understand what it means to fall. You understand what it means for something to be heavy. You understand the idea that light travels, that it takes time to get somewhere, that it can be bent or blocked. Everything tonight is going to be built out of pieces like these, ordinary experiences stretched to unusual extremes, rather than some separate alien logic that has nothing to do with your daily life. Here's a small preview of that approach, just so you can feel the shape of it. Imagine you're standing at the edge of a swimming pool, and someone turns on a drain at the bottom. Near the edges, the water moves lazily, barely stirring. But as you get closer to the drain itself, the water picks up speed, curling faster and faster, until right at the center, it's moving so quickly that anything caught in it simply cannot escape, no matter how hard it tries to swim against the current. A black hole works something like that, except the thing being pulled isn't water, and the drain isn't pulling toward a pipe at the bottom of a pool. It's pulling on the fabric of space itself, and eventually, very close to the center, it's pulling so strongly that not even light, the fastest thing that exists, can swim against the current anymore. That single fact that light itself can get trapped is really the seed from which almost everything else about black holes grows. We'll return to that image many times tonight, turning it slightly each time, adding a little more detail, the way you might turn a stone over in your hand to see it catch the light differently. Over the next several hours of listening, or the next several nights if you'd rather take it slowly, We're going to move through this territory in an order that builds gently rather than jumping around. We'll start by asking a very old, very human question: what actually is gravity at the most basic level before we ever get to anything exotic? We'll talk about how the Earth pulling on you and the Sun pulling on the Earth and a dying star pulling on itself are all, in some sense, the same story told with different amounts of weight and space. From there, we'll ease into the idea of what happens when a massive star runs out of fuel. Because that ordinary, almost mundane process, a star simply running out of things to burn, turns out to be one of the main doorways into black hole formation. There's something quietly moving about that, if you think about it. Something as vast and violent as a black hole can begin with something as unglamorous as a fire going out. Later on, we'll spend real time on the strange geography of a black hole itself, on the idea of an event horizon, which is not a wall or a surface in the way a horizon usually is, but more like a point of no return drawn in empty space. We'll talk about why nothing, not even information, seems able to cross that boundary and come back. And we'll be honest about which parts of that story physicists are confident about, and which parts are still genuinely being argued over in journals and conference rooms even now. That distinction matters to me. I don't want to hand you a tidy, oversimplified myth and call it science. Where there's real uncertainty, I'll tell you so, gently, without turning it into a cliffhanger. We'll also spend time on some of the more delightfully strange consequences, the ones that sound almost like riddles. Why time itself seems to slow down near a black hole for someone watching from a safe distance. Why an object falling might, in some sense, never quite seem to finish falling, at least not from the outside. Why black holes aren't actually cosmic vacuum cleaners hunting down everything nearby, despite how they're sometimes drawn in illustrations. And why the Earth, if the Sun were somehow quietly replaced by a black hole of the same mass tomorrow, would keep orbiting in exactly the same path, just in the cold and the dark. We'll talk about the difference between the small black holes formed from dying stars and the almost incomprehensibly larger ones that sit at the centers of galaxies, including our own, quietly anchoring hundreds of billions of stars in their slow, patient orbits. And we'll talk, near the end, about how we actually know any of this is real, about the astronomers and instruments that manage to detect ripples in space itself, and even to capture something like a photograph of a black hole shadow, a feat that would have seemed like pure fantasy to scientists working just a few generations ago. None of that needs to happen quickly, and none of it needs to happen tonight in your conscious tracking mind. For now, let's just settle back into that gentle downward pull you started with, the ordinary gravity holding you against the mattress, and let it be the doorway into something far larger. Let's go back, then, long before anyone had a word for what we're describing. Long before telescopes, long before anyone had measured the speed of light or written down a single equation about gravity, people already lay on their backs the way you're lying now, looking up at skies that were far darker than almost anyone alive today has ever seen. No estrellitas, no glow from a nearby city bouncing off the clouds. Just thousands of stars, sharp and steady, and a band of hazy light across the middle of the sky that we now call the Milky Way, though for most of human history nobody knew it was made of countless individual suns too far away and too faint to separate with the naked eye. To the people looking up, the dark spaces between those stars weren't empty in any meaningful sense. They were simply unknown. Nobody imagined that hidden in that blackness there might be objects so strange that light itself couldn't climb out of them. That idea, the idea of something so dense and so gravitationally powerful that even light would be pulled back like a stone thrown from a well, wouldn't occur to anyone until gravity itself was understood well enough to ask the question. And that took a very long time. It took, in fact, until the late 17th century, when a man in England sat down and began working out with almost unbearable patience, exactly how objects pull on each other across empty space. That man, of course, was Isaac Newton. You've probably heard the apple story, the one where he supposedly watched an apple fall from a tree and suddenly understood gravity. It's a nice image, and there might even be a kernel of truth buried somewhere in it. But the real work was slower and far less dramatic than a single falling piece of fruit. Newton spent years developing the mathematics needed to describe how the moon stays in orbit around the Earth, how the planets stay in orbit around the sun, and how, remarkably, the same simple rules seem to govern both. One universal law of gravitation, he proposed, reaching across all of space, pulling every object toward every other object, with a strength that depended on how much mass each object had and how far apart they were. It's worth sitting with how strange that idea was at the time. Before Newton, many people assumed the heavens operated by entirely different rules than the ground beneath their feet. The stars and planets belonged to some separate, perfect realm, while apples and rocks and rivers belonged to the ordinary, imperfect world of dirt and decay. Newton's quiet, radical suggestion was that there was no such separation. The same force pulling the apple downward was pulling the moon toward the Earth, and the same force was keeping the Earth from drifting away from the sun. One set of rules everywhere for everything. It's the kind of idea that feels obvious now, something taught early enough in school that its strangeness gets worn smooth, but at the time it reorganized how people understood their place in the universe. Once you have a law of gravity like that, precise enough to calculate with, a very natural question starts to nag at you. If gravity pulls things toward a massive object, how hard would you have to throw something to make it escape that pull entirely? Not just rise for a while and fall back, the way a ball thrown into the air always does, but truly get away, forever, never to return. This is the idea we now call escape velocity, and it turns out to be a beautifully simple thing to picture, even if the mathematics behind it takes some work to unravel. Think of standing on the surface of some planet and throwing a ball straight up. Throw it gently, and it rises a little and falls back into your hand. Throw it harder, and it goes higher before gravity wins and pulls it down again. Keep throwing harder, and at some point, if you could throw it fast enough, the ball would never fall back at all. It would keep moving outward forever, slowing down as gravity tugged on it the whole way, but never quite slowing to a stop, never quite turning around. That speed, the exact speed at which an object stops falling back and simply keeps going, is the escape velocity. For Earth, it happens to be a little over 11 kilometers per second, which is roughly 40,000 kilometers an hour, far faster than any human arm could throw anything, but well within reach of a rocket. And here's where the story takes its first genuinely eerie turn. More than 2 centuries before anyone would use the phrase black hole. In 1783, an English clergyman and natural philosopher named John Michel was thinking about exactly this idea, escape velocity, and he pushed the thought a little further than anyone had before. Michel reasoned that escape velocity depends on 2 things: how much mass an object has, and how compact that mass is, meaning how small a space it's squeezed into. Make an object massive enough, or squeeze it down small enough, or both, and the escape velocity needed to get away from it would climb higher and higher. Michel then asked a question that must have felt almost like a private, quiet act of imagination, sitting alone with pen and paper, since there was no way at the time to test it. What if you had a star so massive and so small for its mass that the escape velocity from its surface exceeded the speed of light itself? Newton's physics, and the physics of the time more broadly, had already established that light traveled at a fixed, finite, measurable speed thanks to earlier observations of the moons of Jupiter. So Michel's question wasn't idle fantasy. It was a real calculation built from real numbers that scientists of his era had genuine confidence in. If light itself couldn't reach escape velocity, he reasoned, then it would be pulled back the same way that ball thrown too gently falls back into your hand. A star like that would be, in his words, essentially invisible, not because it had gone dark, but because whatever light it emitted could never actually leave it and travel outward to reach an observer's eye. He called the idea a dark star. A few years later, working independently across the English Channel, the French mathematician Pierre-Simon Laplace arrived at a strikingly similar conclusion, using the same Newtonian framework, the same basic reasoning about mass, size, and escape velocity. Laplace included the idea in some early editions of one of his own works on the system of the world, describing a body so large that its own light could not escape it, only to remove the passage from later editions. Whether out of scientific caution or simply changing priorities isn't entirely clear from the historical record. Either way, the idea of a dark star, invisible not through absence, but through gravity so intense that light itself became a captive, had been proposed, calculated, and quietly set aside more than 100 years before anyone had the physics needed to actually make sense of it. And that's an important thing to notice, lying here in the dark tonight. Michel and Laplace weren't wrong, exactly, but they weren't quite right either, and the reason why is subtle. They were using Newton's picture of gravity, which treats light as though it were a stream of tiny particles, obeying the same rules as thrown balls and orbiting planets, something that could be slowed down and pulled back by gravity in exactly the way a cannonball can. But light, it would turn out roughly a century and a half later, doesn't quite behave that way. Light always travels at the same speed, no matter how hard gravity pulls on it, no matter how fast the source of that light might be moving. That single, strange fact would eventually force a complete rebuilding of how gravity itself was understood, work that wouldn't fall to Newton's equations at all, but to a young patent clerk in Switzerland, thinking, in his own quiet, patient way, about clocks and falling elevators and the true, curved shape of space itself. That clerk's name, of course, was Albert Einstein, and the questions he was turning over in his mind, quietly, for years, arose from something almost embarrassingly simple. Imagine standing in a closed box with no windows, no way to look outside. If you feel your feet pressed to the floor, is that because the box is sitting still on the surface of a planet, held down by gravity, or because some engine is dragging the box upward through space at a steady acceleration? Einstein realized that there is no experiment you could run inside that box that would tell the difference. Gravity and acceleration, felt from the inside, are the same thing. He called this his happiest thought, and it became the seed of everything that followed. If gravity and acceleration are indistinguishable, then gravity cannot simply be a force reaching out from one mass to another, the way Newton had imagined it, some invisible string pulling the moon toward the Earth across empty space. It has to be something else, something built into the very shape of the space and time through which objects move. This is worth sitting with slowly, because it's easy to let the language slip into something more mystical than it needs to be. When people say that mass curves space-time, it can sound as though space is a kind of cloth, a physical material stretched out like a trampoline, with heavy balls sitting in dips they've pressed into the fabric. That image helps a little, but it also misleads because it invites you to ask what the fabric is made of, what it's stretching into, questions that don't really have answers because space isn't a substance in that sense at all. What curvature actually means in Einstein's theory is something more precise and a little less picturable. It means that the ordinary rules of geometry, the rules you learned about triangles and parallel lines, the rules that work perfectly well on a flat sheet of paper, stop giving the right answers near a large mass. Two beams of light sent out parallel to each other near a star will not stay parallel. The shortest path between 2 points is no longer a straight line in the familiar sense, but a gently bent one, a path called a geodesic. Time itself runs at very slightly different rates depending on how deep you are in a gravitational well, a fact so real that the satellites overhead, right now, quietly correcting your phone's GPS position, have to account for it every single day, or the whole system would drift off by miles within hours. Curved space-time isn't a metaphor standing in for gravity. In Einstein's picture, it simply is gravity, the actual geometry that free-falling objects and beams of light are obligated to follow. Einstein worked on this idea for roughly a decade, on and off, wrestling with mathematics that was, by his own admission, harder than anything he had used before, borrowing tools from geometry that had been developed decades earlier by mathematicians who never imagined they'd end up describing the universe. He finished the theory, general relativity, in November of 1915, presenting a series of lectures to the Prussian Academy of Sciences in Berlin, refining the equations almost week to week as he went, in a kind of visible, public working out of a problem, which is a slightly unusual way for a scientific breakthrough to unfold. The equations he arrived at were notoriously difficult, a tangled web of 10 interlinked expressions relating the curvature of space-time to the distribution of mass and energy within it. Einstein himself doubted that anyone would find an exact solution anytime soon. He expected that physicists would have to settle for years, maybe decades, for approximate answers, useful only for small, gentle curvatures like the very slight bending of starlight passing near the sun. He was wrong about that, and the person who proved him wrong did so under about as strange a set of circumstances as physics has ever produced. Karl Schwarzschild was a German astronomer, already accomplished, already respected, serving as an artillery officer on the Eastern Front during the First World War, calculating trajectories for German guns while, somewhere in his kit, he carried Einstein's newly published paper. Within a matter of weeks, working essentially in his spare time, in conditions that were cold, dangerous, and about as far from a quiet university office as you could imagine, Schwarzschild found an exact solution to Einstein's equations, a precise mathematical description of the curved space-time surrounding a perfectly round, non-rotating mass. He wrote it up and sent it back to Berlin. Einstein was startled and delighted, and presented Schwarzschild's solution to the Academy himself, since Schwarzschild was still at the front. It's one of those small, quiet, human details buried in the history of physics. The exact geometry that would eventually turn out to describe black holes was worked out by a man scribbling equations between artillery calculations, in a war that would kill him within a year, not from combat, but from a rare autoimmune skin disease he developed while serving, dying in the spring of 1916, only a few months after his solution reached print. What Schwarzschild's solution revealed, when people examined it carefully over the following decades, was something strange folded into the mathematics itself. For an ordinary object, like the sun or the earth, or you, lying here right now, the curvature described by his equations is gentle, and everything about it behaves reasonably. But the equations also described what would happen if all of that mass were compressed down into an impossibly small region, a radius now, called the Schwarzschild radius, different for every mass, a few kilometers for something the mass of the sun, less than a centimeter for something the mass of the earth. Inside that radius, the mathematics doesn't just describe strong gravity. It describes a boundary, a point of no return, a surface where the curvature becomes so extreme that not even light moving directly outward can climb back through it. Cross that boundary, and every path forward, in the geometry Schwarzschild's equations describe, leads inward. Not because some force is grabbing you and pulling you back, the way Michel and Laplace had imagined a stream of light particles being reeled in by gravity, but because the very shape of space and time inside that boundary bends so severely that outward, in any meaningful sense, simply stops being a direction you can travel. This is the deep difference between the old dark star and the true black hole, and it's worth turning over slowly before sleep takes you further. It isn't that gravity got strong enough to catch light the way a strong wind catches a bird. It's that space-time itself, the underlying structure in which all motion happens, becomes so warped that the usual distinction between moving through space and moving through time starts to break down. Falling toward the center stops being something you choose to do and becomes something more like the passage of time itself, unavoidable, one-directional, built into the geometry rather than imposed by any external force reaching out to grab you. Nobody, not even Einstein, initially believed this mathematical curiosity described anything that could actually exist in nature. Schwarzschild's solution sat for years, treated by most physicists as an elegant but probably unphysical exercise, an interesting corner of the equations that surely nature would find some way to avoid. It would take the careful, sometimes contentious work of another generation of physicists to start asking a much more uncomfortable question: whether a real star, made of real matter, held up against its own weight only by the pressure of its own furnace, might actually be capable of collapsing all the way down into that strange boundary Schwarzschild had found hiding in the mathematics. To answer that question honestly, you have to start with something almost tender, the ordinary life of a star, and how patiently it holds itself together against the battle it is, in the end, always destined to lose. A star, at its simplest, is a standoff, and like most standoffs, it is quieter than you'd expect from the outside. Deep in its core, hydrogen nuclei are being crushed together with such force and heat that they fuse into helium, releasing energy that pushes outward as light and heat and pressure. Meanwhile, the star's own enormous mass is pulling inward, trying to collapse the whole structure down to a single point. For most of a star's life, these two forces are so exquisitely matched that the star simply sits there, burning steadily, sometimes for millions of years, sometimes for billions, a fire that holds its own shape only because it is falling and burning at exactly the same rate, instant after instant, for as long as the fuel allows. Think of a tightrope walker who never actually stops wobbling, whose arms are in constant, tiny motion, correcting left, correcting right, and yet whose corrections are so continuous and so precise that from any distance at all they appear perfectly still, a picture of calm balanced on top of ceaseless adjustment. That is a star in what astronomers call its main sequence, the long, stable middle chapter of its story, the part that looks, from Earth, like changelessness itself. But fuel runs out. This is the part of the story that never changes, only its pacing does. Once a star exhausts the hydrogen in its core, the balance starts to tip, and what happens next depends almost entirely on one number: how much mass the star had to begin with. It's a strange thing to sit with in the dark, that the fate of a star, whether it fades gently or ends in violence, whether it becomes a smoldering ember cooling for eternity or tears itself apart in a flash brighter than its entire home galaxy, was mostly decided at its birth, quietly, by how much stellar material happened to gather together in that particular cloud of gas and dust. Long before the star had done anything at all, before it had even begun to shine. Stars something like the size of our sun, and smaller, go relatively gently into their decline. As the hydrogen fuel dwindles, the core contracts and heats further, allowing helium to fuse in turn, and the outer layers swell outward into a red giant, puffing off gas in slow, sighing waves that drift outward into space like breath on a cold morning. Eventually, what's left behind is a dense, glowing ember called a white dwarf, an object roughly the mass of the sun squeezed into a sphere about the size of the Earth, a whole star's worth of matter folded down into something you could, in principle, drive across in a few days. It's held up not by fusion anymore, since the fire has gone out, but by something far stranger, a quantum mechanical resistance among the star's own electrons. Physicists call it electron degeneracy pressure, and the basic idea, though the mathematics behind it is subtle, is that certain particles simply refuse to be crowded into the same state as their neighbors. Squeeze them close enough, and they push back, not because they repel each other in the ordinary electric sense, the way two magnets shove apart, but because the rules of quantum mechanics forbid them from all occupying the same tiny space in the same way at the same time. It's a bit like a crowded elevator where every passenger insists on standing in a slightly different posture, angled just so, no matter how tightly they're packed in, and that stubborn, quiet insistence on variety turns out to be load-bearing, holding the whole car upright. This resistance is remarkably strong, but it isn't limitless. In the 1930s, a young Indian astrophysicist named Subramanya Chandrasekhar, working through the mathematics during a long sea voyage from India to England, a journey of some weeks with little to do but think, calculated that there is a ceiling to how much mass a white dwarf can have before even this quantum pressure gives way. Above roughly 1.5 times the mass of the Sun, electron degeneracy pressure simply isn't strong enough to hold the star up any longer, no matter how tightly its electrons resist. Chandrasekhar was in his early 20s when he worked this out, and when he presented it to the Royal Astronomical Society in London, the eminent astronomer Arthur Eddington, whose own earlier expedition to observe a solar eclipse had helped confirm one of Einstein's predictions about the bending of starlight around the Sun, stood up and publicly dismissed the young man's idea as absurd, something nature would surely find a way to prevent. It took decades, and the humbling patience of watching later observations bear the young man out again and again, before Chandrasekhar's limit was accepted as one of the genuine load-bearing numbers of stellar physics, as fundamental in its way as the speed of light. It's a small, quiet lesson in itself, one worth carrying with you into sleep. Sometimes the person in the room with the most experience is still wrong, and sometimes a person still in their 20s has already seen further than anyone else present. So what happens above that mass? This is where stars stop fading gently and start, instead, to detonate. A star considerably more massive than the Sun burns through its hydrogen far more quickly, in a hurry it can't help, then goes on fusing helium into carbon, carbon into oxygen, and so on up through the periodic table, layer by layer, like an onion built in reverse, each layer a heavier element than the one before, each stage burning faster and hotter and shorter than the last, until the whole star resembles something like a set of nested shells, each one a different chemical furnace. This process runs, eventually, into iron. Iron is special in a rather unwelcome way. Fusing lighter elements releases energy, but fusing iron doesn't release energy. It consumes it, draws it in rather than giving it out. So once a massive star's core turns to iron, the fire simply cannot continue, no matter how much pressure or heat is available. The furnace that has held the star up for millions of years goes out within moments, almost soundlessly, and the core, no longer supported by the outward push of fusion, collapses under its own gravity with terrifying speed, falling in on itself in well under a second, a length of time shorter than it takes to draw a single breath. What happens next is one of the most violent events the universe produces. The core collapses so fast and so hard that it rebounds, like a spring compressed past its limit, sending a shock wave tearing back out through the star's outer layers, and the whole star detonates in a supernova, briefly outshining every other star in its home galaxy combined, a single point of light visible for a few weeks across billions of light years. This is not simply a bigger version of the Sun's gentle fade at the end of its life. It's an explosion that forges many of the heavier elements found in your own body, the calcium in your bones, the iron carrying oxygen through your blood right now, elements that were literally cooked inside the dying heart of some ancient star and then flung outward into the space that would, ages later, gather and cool and eventually become part of you, part of the hand you might have resting on your chest as you listen to this. What's left behind at the center of that explosion depends again on mass. If the collapsing core is somewhere between about 1 and a bit and roughly 2 to 3 times the mass of the sun, the collapse halts an even stranger stage than the white dwarf. The protons and electrons in the core get squeezed together so violently that they merge into neutrons, and the whole core becomes an object made almost entirely of neutrons packed as tightly as the nucleus of an atom. An entire star's worth of mass condensed into a sphere perhaps 12 or so miles across, roughly the size of a city, so dense that a single teaspoon of it would outweigh a mountain. This is a neutron star, and it is held up by its own version of the quantum standoff, neutron degeneracy pressure this time, a resistance among neutrons themselves against being crowded any closer together, the same stubborn refusal to share space, just one layer further down. The physicists Walter Baade and Fritz Zwicky proposed the existence of neutron stars in 1934. Remarkably, only 2 years after the neutron itself had even been discovered in a laboratory, reasoning their way toward an object nobody had any direct evidence for yet, purely by following the logic of what a collapsing massive star's core would have to become, sketching out an entire class of objects on paper before anyone had seen so much as a hint of one in the sky. But neutron degeneracy pressure, like its electron counterpart, has its own ceiling, its own breaking point beyond which even this stubbornness fails. Physicists Robert Oppenheimer and George Volkoff, building on Chandrasekhar's earlier work, calculated in 1939 that somewhere above roughly 2 to 3 solar masses, even a sphere of tightly packed neutrons cannot resist its own gravity any longer, and the crowded elevator, so to speak, finally gives way entirely. Beyond that threshold, there is, as far as anyone has ever discovered, no known force left in physics capable of halting the collapse. And so the collapse continues, unimpeded, gravity winning against every resistance physics has to offer. What forms at the end of that collapse is the object this entire exploration has been circling around from the start, a black hole. And the first thing to understand about a black hole is that the black hole itself, in the sense of the collapsed matter, is almost beside the point. What matters, what defines the object entirely from the outside, is a boundary in space called the event horizon. It helps to know that this boundary was discovered mathematically decades before anyone understood what it meant. In late 1915, Einstein published his equations of general relativity, a set of relationships so complicated that Einstein himself doubted anyone would find an exact solution to them for years. Within weeks, a German astronomer named Karl Schwarzschild did exactly that. At the time, Schwarzschild was serving as an artillery officer on the Russian front during the First World War, calculating trajectories for the German army by day, and in whatever time remained, working out the curvature of space-time around a single spherical mass. He mailed his solution to Einstein from the trenches. Einstein was startled by it, presented it to the Prussian Academy on Schwarzschild's behalf, and within a matter of months, the man who had solved his equations more elegantly than he had was dead of a rare autoimmune skin disease he'd contracted at the front. He never learned what his own solution truly implied. Buried inside Schwarzschild's neat, exact description of the space around a mass was a peculiar boundary, a specific distance from the center depending only on how much mass was involved, where the mathematics seemed to break down. For the Sun, that distance would be about 2 miles from the very center. For the Earth, it would be less than an inch. For most of the 20th century, physicists treated this as a mathematical curiosity, an artifact of the equations rather than anything physically real, in part because no ordinary object is ever compressed small enough for that boundary to actually exist outside its own solid material. It took the collapse of Oppenheimer and Foucault's crushed stellar cores, with nothing left to hold them up, to make that boundary into something an object could actually reach. So what is the event horizon? Physically, it is not a surface. There is no wall there, no shell, no membrane, nothing solid to strike. If you have been picturing it as something like the surface of a planet, something you would feel yourself hit, it may help to let go of that image now. The event horizon is better understood as the place where space itself is falling inward toward the center, faster than light can travel outward against it. Imagine a wide, slow river that gradually narrows and speeds up as it approaches a waterfall. A fish far upstream can swim against the current easily. Closer to the falls, the current picks up, and the fish has to work harder to hold its position or make headway back upstream. At some exact point, the current becomes faster than the fastest the fish could ever possibly swim. Past that point, no matter how hard the fish swims, is going over the falls. That point is not marked by anything visible in the water. There's no line, no ripple, no change in the color of the river. It's simply where the math of speed and current cross over into inevitability. The event horizon is something like that line, except the current is space itself, and the speed limit is the speed of light, the fastest anything or any signal or any information can ever travel. This has a strange consequence, one of the strangest and most carefully studied ideas in all of black hole physics. What an event horizon feels like depends entirely on who's asking. Picture an astronaut falling feet first toward a very large black hole, one massive enough that the tidal stretching wouldn't tear her apart before she got close. As she approaches the horizon, from her own point of view, floating in free fall, she notices nothing special happening at all. No bump, no video, no flash of light, no wall of energy, no sensation of crossing a threshold. This isn't a strange exception. It's a direct consequence of one of the oldest ideas in general relativity, the same idea Einstein once described as the happiest thought of his life. A person in free fall cannot locally distinguish their situation from simply floating in empty space, because gravity, locally, doesn't feel like anything at all. It only reveals itself over distances, in a slight stretching and squeezing of tidal forces, not in some dramatic threshold effect at the horizon itself. She would check her instruments, glance at her own wristwatch, and by every measurement she could make in her own little bubble of space, everything would seem entirely ordinary. She would cross the horizon, whatever that means, without a single alarm going off. It's only afterward, once she is already inside, that the situation becomes irreversible. She wouldn't know the exact moment it happened. Now, picture a second observer, a colleague watching from a safe distance through a telescope, patient enough to watch the whole thing unfold. To this distant observer, something very different appears to happen, and it has to do with gravity's effect on both light and on time itself. As the astronaut falls closer and closer to the horizon, the light from her spacesuit, from her instrument panel, from any signal she sends back, has to climb its way back out of an increasingly steep well of curved spacetime. Climbing out of that well costs the light energy, and light that loses energy shifts toward longer, redder wavelengths, a gravitational redshift. At the same time, from the outside observer's perspective, her clock appears to run slower and slower the closer she gets to the horizon, an effect called gravitational time dilation, closely related to the time dilation of relativity's more famous cousin, special relativity, but here caused by the depth of the gravitational well rather than by speed alone. To her distant colleague, she would appear to fall more and more slowly as she approached the horizon, her image growing dimmer and redder, stretching out toward an ever slower crawl, without, according to that outside clock, ever quite visibly finishing the crossing. She would seem to freeze, fade, and eventually vanish from detectability, without the telescope ever recording the precise instant she passed through. Here is the part worth sitting with for a moment, because it sounds like a contradiction and isn't one. Both descriptions are correct. They are not competing claims about what really happens, with one observer simply mistaken. They are two honest accounts, built from two different systems of keeping time of the very same event. It took physicists years to fully untangle this, and one particular turning point came in 1958, when a physicist named David Finkelstein showed that the seeming freeze frame at the horizon was an artifact of the particular way Schwarzschild coordinates had been set up, not a true physical barrier at all. In a different, better-chosen coordinate system, the one that actually tracks a falling observer's own experience, there is no lingering, no freezing, no infinite delay. The falling astronaut sails through in perfectly finite time by her own clock. The horizon is, in this specific sense, locally unremarkable. Nothing marks the spot, and yet, globally, for the whole future of anything that crosses it, the horizon is the most decisive boundary in the universe, because once inside, every possible direction any future path could take, every direction that used to be called forward in time, now points only further in toward the center with no path left leading back out. It isn't a wall keeping her in. It's more like a river that no longer offers a route upstream in any direction at any speed ever again. And that raises the natural question of what exactly waits at the end of that one-way current, down where all those inward-pointing paths are eventually heading. The honest answer is that physics gets quieter and more careful the closer it looks, and it's worth understanding why, rather than skipping past it towards something more dramatic. Start with what happens on the way down, because that part is on much firmer ground. Gravity, remember, isn't a single uniform pull. It's stronger the closer you are to whatever is doing the pulling, which means that if you're falling feet first toward a black hole, your feet, being near the center, feel a stronger pull than your head does. The difference is small when you're far away, so small you'd never notice it's standing on Earth, where your feet are only about 2 meters closer to the planet's center than your head. But near a black hole, especially a small one, that difference in pull from one end of your body to the other can become enormous, because the gravity there changes so sharply over such short distances. Your feet get yanked forward harder than your head, so your body gets stretched lengthwise like a piece of taffy being pulled from both ends. At the same time, your left and right sides get squeezed inward because the paths pulling them toward the center are converging, all aiming at the same point. The way lines drawn to the vanishing point of a picture converge as they approach it. Stretched long, squeezed thin. Physicists, with a fondness for vivid shorthand that occasionally slips out of the lecture hall and into the wider world, took to calling this process spaghettification, and the name stuck, half a joke and half a genuinely useful mental picture, because that is more or less the shape a falling body would be reduced to if it fell toward a small enough black hole for the tidal stretching to overwhelm it before it crossed the horizon at all. For a very large black hole, one with a horizon spanning millions of kilometers, the stretching near the horizon can be gentle enough that nothing dramatic happens right at the boundary. The astronaut of the last section might cross over feeling nothing unusual at all. It's only deeper in further along that inward current that the tides would eventually tighten their grip. And that inward current leads, according to Einstein's equations taken at face value, to a place where the mathematics stops behaving. For a black hole that isn't spinning, the equations predict that all the paths converging toward the center meet at a single point, where the tidal stretching becomes infinite, where the curvature of spacetime itself is described by numbers that simply blow up rather than settling on any finite value. This is the singularity, And it's worth being careful about what that word is and isn't claiming. It doesn't mean a tiny, unimaginably dense object sitting at the center, waiting the way a stone sits at the bottom of a well. In fact, inside the horizon of a non-spinning black hole, something stranger happens to the geometry. The roles of space and time partially trade places, so that moving toward the center stops being like moving toward a location and starts being more like moving forward in time. The singularity isn't a place you approach. It's closer to a moment, a final moment, that every inward path is heading toward the way every path through an ordinary day is heading toward tomorrow, unavoidably, just by the nature of what time does. That reframing helps explain something that puzzles people. Why nothing, not even light, can avoid it, and why asking what's at the singularity is a little like asking what's at next Tuesday. It isn't a location to be visited. It's closer to a destination that the flow of time itself is carrying you toward. For years, some physicists suspected that this singularity might just be a quirk of the perfectly symmetrical, idealized case Carl Schwarzschild had solved back in 1916, a mathematical convenience that wouldn't survive contact with a Messier, more realistic collapsing star. That hope was closed off in 1965, when a mathematician and physicist Roger Penrose proved, using very general reasoning rather than any special symmetry, that once a certain kind of trapped surface forms during collapse, a singularity is essentially unavoidable under the assumptions of general relativity. It wasn't a special case. It was a consequence of the theory itself, holding up no matter how lumpy or imperfect the collapsing object happened to be. That work, decades later, was part of why Penrose was awarded a share of the 2020 Nobel Prize in Physics. Now, most black holes in the actual universe are not perfectly still. They form from stars that were already spinning, and the collapse tends to concentrate that spin rather than erase it, the way a skater pulls in their arms and spins faster. A rotating black hole behaves differently in some genuinely important ways, and the mathematics describing it wasn't solved until 1963, when a New Zealand mathematician named Roy Kerr found an exact solution to Einstein's equations for the spinning case, nearly 50 years after Schwarzschild found the non-spinning one. In Kerr's solution, the singularity isn't a point at all, but a ring, and the spin drags the surrounding space-time around with it, the way stirring a spoon through honey drags the honey along in a swirl, even at some distance from the spoon itself. Close enough to a spinning black hole, this dragging becomes so strong that no object, no matter how powerful its engines, can hold still relative to the distant stars. It gets swept along in the rotation whether it wants to or not. This region, lying just outside the horizon itself, is called the ergosphere, and its boundary is shaped less like a sphere and more like a flattened, pumpkin-like curve, bulging out furthest at the black hole's equator. The ergosphere has one more peculiar and, in principle, useful property. Because it lies outside the horizon, objects that enter it can still escape, unlike anything that crosses the true point of no return. In 1969, Roger Penrose described a thought experiment showing that an object entering the ergosphere, splitting into two pieces, and having one piece fall inward while the other escapes, could come out again carrying more energy than it went in with the difference drawn from the black hole's own rotational energy gradually slowing its spin. Nobody has built such a machine, and nature would need very particular conditions to run the process on its own, but it stands as a real, calculated consequence of the equations, a reminder that even the region just outside a black hole holds physics with no everyday counterpart. It's worth pausing here, though, to be honest about where careful science ends and speculation would begin. Everything just described, the stretching, the ring singularity, the ergosphere, the Penrose process, comes from general relativity, a theory that has passed every test thrown at it for over a century. But general relativity is a theory of smooth, continuous spacetime, and most physicists suspect it cannot be the final word on what actually happens at a singularity, because the same equations that predict the singularity also predict their own breakdown there, spitting out infinities that almost certainly signal the theory has been pushed past its rightful domain rather than describing anything physically real. What actually replaces that infinity? Whether some future theory uniting gravity with quantum mechanics smooths it into something finite, remains genuinely unresolved, and treating any particular proposal as settled fact would be overstating the case. There's also an unresolved question, still debated among researchers, about whether the interior structure of a real, rotating black hole even resembles Kerr's tidy ring singularity, since some calculations suggest the inner regions may be unstable in ways that complicate that clean picture. So the interior remains, quite honestly, one of the places where physics knows the shape of its own ignorance clearly enough to draw a careful boundary around it, and knows better than to pretend otherwise. What's less uncertain, and in some ways more remarkable, is what a black hole does not on its way in, but slowly, over unfathomable stretches of time, on its way toward eventually fading away entirely. But before that story of fading can be told properly, it helps to understand what a black hole actually spends most of its existence doing. Left alone in the depths of space, with nothing nearby to disturb it, a black hole is genuinely dark. No light, no signal, nothing to see. And yet some of the most luminous objects ever detected in the universe, sources so bright they outshine entire galaxies of hundreds of billions of stars, are powered by black holes. That is not a contradiction once you understand what actually produces the light. It isn't the black hole itself glowing. It's everything the black hole is pulling in, screaming and heating and radiating on its way down, before it ever reaches the point of no return. Picture water spiraling down a bathtub drain. It rarely goes straight in. It circles first, because even a small sideways motion, a little bit of what physicists call angular momentum, has to go somewhere, and the water can't simply erase it. The same is true of gas, dust, and shredded stellar material falling toward a black hole. Almost nothing falls in a straight line. Instead, it settles into a flattened, spinning structure called an accretion disk, matter orbiting the black hole the way water swirls around a drain, gradually working its way inward. As that material spirals closer, something else happens that resembles a figure skater pulling in their arms. An ice skater spinning slowly with arms outstretched will spin dramatically faster the moment they draw their arms to their chest, because the total spin, the angular momentum, has to be conserved even as the shape changes. Infalling gas behaves similarly. As it moves inward through the disk, it's forced into a smaller and smaller orbit, and it has to spin faster to conserve that angular momentum. Neighboring streams of gas, now moving at different speeds, rub against each other. That friction, that constant subtle grinding of gas against gas, converts orbital energy into heat, and it's an extraordinarily effective process. The gas in the innermost part of the disk, closest to the black hole, can reach temperatures of millions of degrees, hotter than the surface of most stars by a wide margin. Anything heated to that degree radiates light, and the color of that light depends on temperature the same way a blacksmith's iron does. Cooler iron glows a dull red. Heat it further, and it turns orange, then yellow, then a blinding white. Push the temperature high enough, past anything achievable in a forge, and the emitted light shifts entirely out of the visible range into higher energy wavelengths we can't see with our eyes at all, ultraviolet, and then X-rays. That's exactly what happens in the inner accretion disk around a black hole. It becomes hot enough that it shines primarily in X-rays, which is, in fact, one of the main ways astronomers find black holes in the first place. They can't see the black hole. They see the X-ray glow of the tortured, superheated gas circling just outside it. What makes this especially efficient, more efficient than almost any other energy-producing process known, is how much of the infalling matter's mass gets converted into radiated energy before it disappears across the horizon. Nuclear fusion, the process that powers stars and lights up the night sky one star at a time, converts less than 1% of the mass involved into energy. The rest stays locked up as matter. Accretion onto a black hole can convert somewhere between 10 and 40% of the infalling mass into radiated energy, depending on how the black hole spins and how the disk is arranged. That's an enormous difference. A relatively modest amount of gas, funneled into a black hole's accretion disk, can outshine the fusion output of an entire galaxy of ordinary stars. The black hole isn't creating that energy out of nothing. It's simply an extraordinarily deep gravitational trap, and matter falling into a deep trap releases a great deal of energy on the way down, in the same way a ball dropped from a great height hits the ground harder than one dropped from a windowsill. Except here the trap is so deep that a meaningful fraction of the very mass of the object is converted directly into light. The disk isn't the only feature that develops around an actively feeding black hole. Many of these systems also produce jets, narrow, tightly focused beams of particles blasted outward from the region near the black hole at speeds approaching the speed of light, often shooting out along the black hole spin axis, straight up and straight down from the disk like the poles of a spinning top. These jets can be almost bewilderingly long, stretching for thousands, even millions of light years far outside the galaxy that contains the black hole feeding them, all while remaining remarkably narrow and coherent over that entire distance. The way a well-focused flashlight beam stays a tight column of light, rather than spreading into a useless haze. Exactly how nature manages to keep these jets so narrow and so stable across such staggering distances is still an active area of research. But magnetic fields are understood to play a central role. As charged particles in the disk swirl around the black hole, they drag magnetic field lines along with them, and the black hole's own spin, along with the frame dragging effect described earlier, twists those field lines further, winding them tighter, the way twisting a rope stores energy in the twist itself. That wound-up magnetic structure can act like a slingshot, flinging charged particles outward along the spin axis, and, in some models, even tapping into the rotational energy of the black hole itself to help power the jet, a process related in spirit to the theoretical energy extraction idea described earlier. Only here it's nature actually doing it, using magnetic fields instead of a hypothetical thrown object. When this entire system, the hot disk, the X-ray glow, the towering jets, is scaled up to the size of a supermassive black hole sitting at the center of a galaxy, and when that black hole is actively pulling in large quantities of gas, the resulting object is called a quasar. Quasars were first noticed in the mid-20th century as strange radio sources that, when astronomers pointed optical telescopes at them, appear to be nothing more than ordinary, unremarkable points of light, indistinguishable from nearby stars. That was deeply puzzling because their spectra, the pattern of light they gave off, didn't match anything familiar. The puzzle was resolved in 1963 when the astronomer Martin Schmidt, studying one of these objects, realized that its spectrum did match hydrogen, but only if the light had been stretched, redshifted, by an extraordinary amount, meaning the object was retreating from us at tremendous speed as part of the universe's overall expansion, which meant, in turn, that it had to be billions of light years away. An object that faint-looking, at that almost inconceivable distance, would have to be intrinsically brighter than an entire galaxy just to be visible at all. That was the moment astronomers realized they weren't looking at a strange nearby star. They were looking at the light-up signature of a supermassive black hole, feeding at the heart of a young and distant galaxy. So the brightest, most energetic objects known in the universe turn out to be powered by the darkest ones. The black hole itself contributes nothing to the light directly. It is simply the deep well that the matter falls into, and the fire is lit entirely by the matter's own descent, its own friction, its own heat, all of it radiated away in the moments before that matter vanishes across the horizon for good. It's a strange and rather beautiful inversion, worth sitting with for a moment. An absence at the center, and yet, gathered around that absence, some of the most searing brilliance the cosmos has ever produced. With that picture of a feeding, glowing black hole in mind, it's worth turning next to the real objects astronomers have actually found this way, much closer to home than any distant quasar. Take Cygnus X, one, for instance, a name that sounds cold and technical, but belongs to one of the oldest and most convincing black hole detections we have. In the early 1960s, a rocket-borne detector briefly above the atmosphere picked up a source of X-rays coming from the direction of the constellation Cygnus, the Swan. X-rays don't reach the ground. The atmosphere absorbs them, which is fortunate for us but inconvenient for astronomers, who spent years chasing this source with better and better instruments, eventually pinning it down to a specific patch of sky. What they found there, when they looked with ordinary optical telescopes, was a single blue supergiant star, massive and hot, orbiting something. The star itself couldn't produce X-rays like that, but its motion gave it away. By watching the star's light shift back and forth, redder and bluer, in a steady rhythm, astronomers could tell it was being tugged by a companion, something with enough gravity to swing a supergiant around a shared center of mass every 5.5 days. And when they calculated the mass of that unseen companion from the orbit alone, using nothing but Newton's old equations for how gravity governs motion, the answer came out far too large for a normal star and far too compact to be anything but a black hole. It was invisible in the most literal sense. It gave off no light of its own, but its gravity left fingerprints everywhere around it, in the wobble of its companion, in the fierce X-ray glow of gas being pulled from that companion's outer layers and heated to tens of millions of degrees on its way down. Even Stephen Hawking, who was famously skeptical about Cygnus X-1 for years, made a friendly wager with a fellow physicist that it wasn't a black hole at all, a bet he conceded in 1990 after the evidence became simply too strong to keep betting against. This is really the heart of how black holes get discovered. Nobody has ever pointed a telescope at empty space and watched a black hole appear. What astronomers do, instead, is notice something behaving strangely and then work backward to explain that strangeness. It's a bit like being in a dark room and knowing there's a heavy piece of furniture nearby, not because you can see it, but because you keep stubbing your toe on it in the same spot. The furniture is invisible, but its effects are entirely consistent and repeatable, and after enough stubbed toes, you'd be foolish to deny it's there. Gravity is the toe stubbing, in this analogy, and astronomers have gotten remarkably good at cataloging every way gravity can announce the presence of something otherwise unseeable. Orbital motion is the oldest and most trusted of these methods, the same one used for Cygnus X-1, and it works because Isaac Newton figured out, more than 3 centuries ago, a precise relationship between how fast something orbits, how far it orbits from its companion, and how much mass that companion must have. It doesn't matter whether the companion is a star, a planet, or a black hole. The equations don't care what the object is made of, only how much of it there is. So if astronomers can watch a star swing around some invisible point in space, timing its orbit and measuring its distance, they can calculate the mass of whatever it's swinging around with real confidence. If that mass turns out to be several times the mass of the sun, but the region it's crammed into is too small to be a star, too small even to be a dead, collapsed stellar remnant like a neutron star, then a black hole becomes not just the most likely explanation, but often the only explanation that fits without breaking known physics. Radiation is the second method, and this is where the drama tends to happen. Black holes themselves are dark, but the material spiraling toward them very much is not. As gas and dust are pulled inward, they don't fall straight in the way a stone falls into a pond. Instead, because the infalling material almost always carries some sideways motion, some angular momentum left over from wherever it came from, it spirals inward slowly, flattening out into a wide, glowing disk, the accretion disk mentioned earlier. Friction inside that disk, particles jostling and rubbing against each other as they crowd closer together, heats the gas to searing temperatures, hot enough that it glows not just in visible light, but in ultraviolet and X-rays. That radiation is loud in a cosmic sense. Even a completely dark black hole, thousands of light years away, can announce itself this way as a bright, flickering X-ray source, precisely because of what it's doing to the matter nearby, never because of anything the black hole is doing on its own. The third method is subtler and stranger, and it relies on something Einstein predicted almost as a side effect of general relativity, long before anyone thought it might become a genuinely useful tool. It's called gravitational lensing. Massive objects bend the space around them, and light traveling through that bent space follows a curved path, the same way a marble rolling across a warped table will curve even though nothing is pushing it sideways. If a black hole happens to pass directly between Earth and a more distant star, the black hole's gravity can bend and focus that star's light, briefly making it appear brighter, sometimes even splitting it into multiple faint images before the alignment passes and everything returns to normal. Astronomers have used exactly this effect to detect black holes that give off no radiation at all, ones that aren't feeding, aren't glowing, aren't giving away their presence any other way. All they do is briefly warp the light of a background star, a fleeting flicker that, if you happen to be watching that patch of sky at exactly the right moment with exactly the right instruments, betrays something massive and dark passing quietly through the dark. All three of these methods, orbital motion, radiation, and lensing, came together most dramatically in the case of Sagittarius A star, the object sitting at the exact center of our own galaxy. For decades, astronomers suspected something enormous and compact lived there because the entire galaxy seemed to rotate around that point. But the real proof came from patiently watching individual stars near the galactic center, stars with names like S2, tracking their motion year after year, decade after decade, through clouds of dust that block ordinary visible light but not infrared. What they found was almost startling. These stars were whipping around an invisible point at astonishing speeds, one of them completing an entire orbit in only about 16 years, swinging as close to that central point as our solar system's own planets swing around the sun, and yet moving fast enough at the closest approach to cross a significant fraction of the distance light travels in a day, within just a few hours. From those orbits, astronomers calculated the mass required to hold such stars on such tight, fast paths, and a number that came out was about 4 million times the mass of our sun, all packed into a region no larger than our solar system. Nothing except a black hole fits that description. The work confirming this, painstaking decades of infrared observation from ground-based telescopes, earned Reinhard Genzel and Andrea Ghez a share of the 2020 Nobel Prize in Physics, awarded specifically for demonstrating, through years of careful stellar tracking, that a supermassive black hole really does sit at the heart of the Milky Way. And then, in 2022, came something even more direct. The Event Horizon Telescope, the same global collaboration that had already produced an image of the black hole in the galaxy M87, turned its attention to Sagittarius A star itself and produced a picture, an actual image, of the glowing ring of gas surrounding its dark center. It's worth pausing on how strange this achievement really is. It's worth pausing on how strange this achievement really is. A black hole itself emits no light, casts no glow, offers nothing for a telescope to catch. What the Event Horizon Telescope actually captured was the shadow, a dark circle cast against the bright, swirling gas falling toward the black hole. Gas heated to such extremes that it radiates in radio waves, the same general kind of wave that carries a station across your car radio, just tuned to a frequency far beyond what human ears or eyes could ever process directly. To make that image, astronomers linked observatories across the entire planet, from Hawaii to Spain to Antarctica, and had them all watch Sagittarius A star at precisely the same moments, effectively turning Earth itself into a single telescope the size of our whole world. That was the only way to gather enough detail to resolve something so small and so far away. And even then, the picture took years to process because Sagittarius A star's gas changes on a timescale of minutes, faster than the light from opposite sides of the Earth even takes to compare, so the team had to develop entirely new mathematical methods just to average out that flickering and pull a stable image from a noise. What emerged matched, with remarkable precision, what Einstein's equations had predicted a century earlier: a bright ring bent by gravity, dark at the center, exactly the shape theory said a black hole's shadow ought to have. So light, in its various forms, gave us these two extraordinary confirmations, one from patiently tracking stars, one from photographing a shadow. But there is another way that black holes make themselves known to us, one that doesn't rely on light at all. And it comes from something Einstein predicted but privately doubted anyone would ever actually detect. That something is a gravitational wave, and to understand what it is, it helps to go back to the idea of space-time as a kind of fabric, the same image used earlier to explain how mass creates the curves that we call gravity. If you picture space-time as a stretched sheet and a heavy object as a bowling ball resting on that sheet, creating a dip that other objects roll toward, then imagine what happens if two very heavy objects begin circling each other, closer and closer, faster and faster. They don't just sit in their dips. They churn the fabric around them. And Einstein's equations showed that this churning doesn't stay put near its source, the way ripples in a pond eventually still. Instead, the disturbance itself travels outward at the speed of light, stretching and squeezing space as it goes, ever so slightly in a rhythmic pattern. This is a gravitational wave. It is not a wave of anything moving through space. It is a wave in space itself, a genuine ripple in the geometry of the universe, passing through you right now. In fact, from countless distant sources, though so faintly that it changes the distance between your two hands by an amount many trillion times smaller than the width of a single atom. That faintness is precisely why Einstein doubted these waves would ever be observed, even though his own mathematics predicted them in 1916. The effect seemed simply too small to ever measure, buried far beneath the reach of any instrument he could imagine. For nearly a century, that assumption held. Then, in the early 2000s, physicists in the United States finished building an instrument specifically designed to try anyway, a project called LIGO, the Laser Interferometer Gravitational Wave Observatory. Its design is almost deceptively simple to describe, even though building it was one of the most demanding engineering efforts in the history of science. Picture two long tunnels, each about 2.5 miles long, arranged in an L shape, with a laser beam split and sent down each tunnel, bounced off a mirror at the far end, and brought back to recombine. Under normal conditions, the two light beams cancel each other out in a precise way, tuned so that no light reaches the detector at all. But if a gravitational wave passes through, it stretches one tunnel by an infinitesimal amount while squeezing the other just briefly, just barely, and that tiny mismatch lets a flicker of light through where there should be none. To catch a signal that small, the LIGO team had to isolate their mirrors from virtually every source of vibration on Earth, from distant traffic to ocean waves crashing on shorelines hundreds of miles away, from the swaying of trees in wind to the subtle trembling caused by logging trucks passing on nearby roads. They built two identical detectors, one in Louisiana and one in Washington state, separated by roughly 2,000 miles, specifically so that a real gravitational wave arriving from deep space would register in both just moments apart, while random local noise at either site would not repeat in the same pattern at both locations. On September 14, 2015, before the instrument had even officially begun its scientific run, both detectors registered the same fleeting signal, a rising chirp lasting a fraction of a second, present in Louisiana, and then, 7 milliseconds later, present in Washington. When physicists analyzed its shape, they found it matched, almost too perfectly, the pattern predicted for two black holes spiraling into each other and merging into one. The source, they calculated, lay over 1 billion light years away, involving two black holes each around 30 times the mass of our Sun, which have been circling each other for ages, drawing closer with every orbit as they radiated away energy in the form of gravitational waves, until in their final moments they were completing an orbit around each other many times per second, faster than a hummingbird beats its wings, before finally colliding and merging into a single, larger black hole. In that final instant, the merger converted an amount of mass equivalent to about 3 suns directly into gravitational wave energy, radiated outward across the universe in far less than a second, briefly outshining, in terms of sheer power, every star and galaxy in the observable universe combined, though entirely invisible to any telescope because none of that energy was light. It traveled instead as pure distortion in the shape of space, crossing over 1 billion years of cosmic distance before finally reaching 2 mirrors on Earth and nudging them by less than the width of a proton. This detection did more than confirm Einstein's century-old prediction. It opened something like a new sense for astronomy, an entirely different way of perceiving the universe, the way adding hearing to a world previously known only through sight might change what you notice about a room. And these gravitational wave signals carry a very particular kind of story within them, one that unfolds in 3 recognizable stages. First comes the inspiral, the long, slow spiral of 2 black holes drawing closer, producing a signal that rises steadily in both pitch and volume, like a whistle tightening as the objects speed up. Then comes the merger itself, the instant of collision, brief and violent, where the signal peaks. And then comes something scientists call the ring down, perhaps the strangest part of the whole event. Immediately after 2 black holes combine, the newly formed single black hole is not yet perfectly smooth. It briefly wobbles and shudders, distorted from the true, simple shape that a black hole eventually settles into. And as it settles, it literally rings, shedding its irregular shape by radiating away more gravitational waves at a frequency and a decay rate that depend only on the final black hole's mass and its spin. It is, in a very real sense, like striking a bell and listening to the tone fade, except the bell is warped space-time itself, and the sound is silent to every sense except the one scientists have only just learned how to build. There is something almost peaceful about that image, a black hole ringing itself into stillness after violence. And it leads naturally into a much quieter, much stranger question that occupied physicists for decades afterward. If a black hole can settle down, can it also eventually fade away entirely? For most of the 20th century, the answer seemed to be a simple no. Black holes were understood as the universe's most perfect one-way doors. Matter and energy could fall in, but by definition, nothing could come back out, not light, not radiation, not even a whisper of information about what had been swallowed. That was, after all, the whole idea of an event horizon. It was a boundary with no exit. Then, in the early 1970s, a young physicist named Jacob Bekenstein began asking an odd question, one that sounded almost like a technicality, but turned out to open an entirely new field. Bekenstein was thinking about entropy, a concept borrowed from thermodynamics that measures, loosely speaking, the disorder or the hidden information content of a system. Every ordinary object has entropy. A shuffled deck of cards has more entropy than a sorted one. A glass of warm water mixed with cold has more entropy than the two temperatures kept separate. And there's a very old, very reliable law of physics, the second law of thermodynamics, which states that the total entropy of a closed system can never decrease. It can stay the same, or it can grow, but it cannot shrink. Bekenstein noticed a problem. Imagine dropping a hot cup of tea into a black hole. That tea carried entropy, real, measurable disorder, and once it crossed the event horizon, it vanished from the observable universe entirely. If the black hole itself had no entropy of its own, then the total entropy of the universe would have simply decreased the moment the tea disappeared, and that would violate one of the most trusted laws in all of physics. So Bekenstein proposed something bold. He suggested that black holes must have entropy too, and that this entropy must be tied to the size of the event horizon itself, specifically to its surface area. The bigger the black hole, the more entropy it holds, the more hidden disorder is locked away behind that boundary. Most physicists at the time found this suggestion troubling, and one of the most prominent skeptics was a young British physicist named Stephen Hawking. Hawking's objection was straightforward and, on its surface, quite reasonable. Anything with entropy, in the standard understanding of thermodynamics, must also have a temperature. And anything with a temperature above absolute zero must radiate energy, the way a hot stove radiates heat you can feel from across a room, or the way your own body, even at rest, glows faintly in infrared light. But a black hole, according to everything understood about general relativity at the time, could not radiate anything at all. Nothing escaped past the event horizon. So how could it possibly have a temperature? Hawking set out, essentially, to prove Bekenstein wrong. Instead, in 1974, after working through the mathematics of what happens to quantum fields near an event horizon, Hawking found the opposite of what he expected. Black holes, he discovered, are not perfectly black after all. They emit a faint, steady stream of particles, now called Hawking radiation, and this radiation carries away energy, which means ever so slowly it carries away mass as well. The explanation lay in the strange behavior of empty space itself at the smallest possible scales. Empty space, according to quantum theory, is never perfectly empty. It seethes with brief, fleeting disturbances, often described as pairs of particles winking into existence and then annihilating each other again almost instantly, borrowing energy from the vacuum so briefly that no law of physics is actually broken. This happens everywhere, constantly, throughout the universe, and it is usually undetectable precisely because these pairs cancel out so quickly. But near the edge of a black hole, something different can happen. If such a pair appears right at the event horizon, it becomes possible for one partner to fall inward while the other escapes outward, before the two ever have the chance to meet again and cancel each other out. To a distant observer, it looks exactly as though the black hole itself has emitted a particle. And because the infalling partner carries negative energy from the perspective of an outside observer, its capture very slightly reduces the mass of the black hole. Repeat this process over enormously long stretches of time, particle after particle, and a black hole slowly, almost imperceptibly, loses mass. It evaporates. The rate of this evaporation depends heavily on size, and here the numbers involved are almost impossible to hold in the mind comfortably. A black hole with the mass of a star radiates Hawking radiation so faintly, at a temperature so far below the background temperature of the universe itself, that it would actually absorb far more energy from the cosmic microwave background than it emits, meaning it would grow rather than shrink, at least for now, at least until the universe cools further. Only much smaller black holes, hypothetical ones far less massive than any star, would radiate hot enough and fast enough to noticeably shrink within any timescale shorter than the current age of the universe. And the very largest black holes, the supermassive ones sitting at galactic centers, are calculated to have temperatures so close to absolute zero and evaporation timescales so staggeringly long, stretching to numbers of years that dwarf the current age of the universe by unimaginable factors, that evaporation is, for all practical purposes, something to be described mathematically rather than something anyone could ever observe directly. This discovery did something remarkable. It connected three previously separate fields of physics, general relativity, quantum mechanics, and thermodynamics, in a single quiet result, suggesting that black holes are not simply cosmic drains, but genuine thermodynamic objects with a real temperature, real entropy, and a real, if extraordinarily slow, lifespan. But it also opened a puzzle that remains, even now, one of the most actively debated questions in theoretical physics, a puzzle usually called the information paradox. Here is the trouble. If a black hole eventually evaporates completely, radiating away every last bit of its mass as Hawking radiation, then eventually nothing remains of it at all. But the radiation Hawking calculated appears to be almost perfectly random, depending only on the black hole's overall mass, spin, and charge, carrying no apparent trace of what specifically fell in to create or feed that black hole. Drop a stack of old letters into a black hole, or drop a chunk of ice of equal mass, and according to the original calculation, the radiation that eventually comes back out looks statistically the same either way. But quantum mechanics, as it is understood almost everywhere else in physics, insists that information cannot simply be destroyed. The universe is thought to be reversible at its deepest level, meaning that, in principle, if you knew everything about a final state, you could always, in theory, work backward and reconstruct the initial state that produced it. If black holes truly erase information completely, that fundamental reversibility breaks down, and nobody has been able to comfortably accept that conclusion, including Hawking himself, who spent decades wrestling with it. It is worth being honest here rather than tidy. This is not a problem that has been solved and quietly filed away. Physicists have proposed numerous ideas over the past 50 years, involving subtle correlations hidden within the radiation, or strange geometric structures at the horizon, or deep connections between spacetime and quantum entanglement that are still being explored through ongoing mathematical research. Some recent calculations, developed over the last several years, suggest that information may in fact be preserved, encoded in ways far more subtle than anyone originally suspected, emerging gradually as a black hole ages rather than being trapped forever. But these are active, contested areas of physics, not settled textbook conclusions, and any honest account of black holes has to leave room for the fact that some of the deepest questions here remain genuinely open. What makes this puzzle so quietly fascinating is what it reveals about black holes as objects to think about while drifting towards sleep. They are not simply cosmic vacuum cleaners, sitting silently in the dark. They are, in their own strange and unhurried way, breathing, faintly, radiating, aging, and perhaps, somewhere in that slow whisper of escaping particles, still holding on to secrets about everything they have ever swallowed. Let's drift now toward the black holes that are hardest to find, The ones that sit at the edges of what astronomers have actually confirmed rather than merely calculated. Settle into this a little more slowly than before, because here the ground gets softer, the evidence thinner, the certainty replaced by careful, patient guesswork. Imagine, for a moment, the universe in its first fraction of a second, not yet cool, not yet smooth, but a churning, uneven soup of energy so dense that ordinary matter had not even finished deciding what it wanted to be. There were no stars yet, no atoms, really in the way we think of them now. Just fluctuations, tiny ripples of density rising and falling within that scalding fog. In that chaotic instant, some physicists suspect tiny regions of space could have been dense enough to collapse directly into black holes, without any star ever forming first, without any of the slow, patient nuclear burning that takes millions of years to build toward collapse. These would be primordial black holes, born not from stellar death, but from the raw unevenness of the newborn cosmos itself. And they could, in principle, have come in almost any size, from something with the mass of a mountain packed into a space smaller than an atom, to something far larger, perhaps rivaling the mass of an asteroid or even a small moon, all compressed down into a point still too small to see. Nobody has ever definitively observed one. They remain, for now, a hypothesis, a reasonable and mathematically consistent idea that would elegantly explain a few cosmic puzzles, including possibly some of the universe's mysterious dark matter, that invisible scaffolding that seems to outweigh all the stars and galaxies combined, and yet refuses to show itself directly. It is an idea still waiting for its evidence, the way a name on an old family tree waits for someone to finally track down the birth certificate. Astronomers have searched for the telltale flickers such black holes might cause, faint gravitational lensing events where a tiny, invisible mass drifts briefly in front of a distant star, bending and brightening its light for a few fleeting hours before moving on into darkness again. A handful of candidate flickers have been recorded over the years, and each time, patient scientists have had to ask whether they were seeing a primordial black hole passing by, or simply an ordinary star doing something ordinary in an unusual way. So far, ordinary explanations have mostly won. The primordial black hole waits, unconfirmed, a shape suggested by shadow, but never yet by substance. If primordial black holes are the ones almost too small and too old to catch, intermediate mass black holes are the ones that are, frustratingly, just the wrong size to find easily. Picture a scale that runs from black holes a few times heavier than our sun, formed from dying stars, up to the supermassive giants that anchor entire galaxies, weighing millions or even billions of times more than the sun. Somewhere in between those two extremes, logically, there ought to be a middle population, black holes of a few hundred to a few 100,000 solar masses, filling in the gap the way a river fills a valley between two mountain ranges. And for a long time, this middle category was almost eerily empty in the observational record, like a missing size on a shelf of shoes that otherwise ran smoothly from small to large, an absence so tidy it almost felt deliberate, though nature rarely arranges itself so neatly by coincidence. Astronomers had good theoretical reasons to expect intermediate mass black holes existed, tucked perhaps in the dense cores of globular star clusters, or drifting in the messy centers of small, unassuming galaxies too faint and too far to study easily. But for decades the direct evidence was thin, more suggestive shadow than solid shape. A rumor passed quietly between researchers rather than a fact printed plainly in the textbooks, that has started to change gradually the way morning light changes a room without anyone noticing the exact moment it happened. Gravitational wave detectors, the same instruments that first caught the ripples from merging stellar mass black holes back in 2015, A detection that itself took decades of patient engineering to achieve, has since picked up signals from mergers involving black holes heavier than any single star could plausibly produce through ordinary collapse. This hints that some black holes grow not just by swallowing gas, but by colliding and combining with each other, stacking up in mass across repeated cosmic collisions, like small snowballs rolling downhill and gathering more snow with every turn, each collision leaving them just a little heavier, a little closer to that mysterious middle range. Separately, sharp-eyed observations of globular clusters, those tight, ancient swarms of hundreds of thousands of stars orbiting on the outskirts of galaxies like quiet, glittering satellites, have revealed subtle gravitational tugs that are hard to explain unless something heavy and invisible sits at the center, pulling nearby stars into faster orbits than gravity from ordinary matter alone would produce. Astronomers measure these orbits the way you might infer the presence of a hidden magnet, by watching how iron filings arrange themselves on a sheet of paper, never seeing the magnet itself, only its unmistakable influence. None of this amounts to a single, unambiguous photograph the way the Event Horizon Telescope produced in 2019 for the supermassive black hole in the galaxy M87, that now famous glowing ring against a dark backdrop. It is closer to detective work, a pattern of fingerprints and footprints strongly suggesting someone was in the room, even without a clear image of their face. This puzzle connects to a much bigger and, in some ways, more startling question, one that has quietly troubled astronomers for years now. How did the truly supermassive black holes, the ones with billions of times the sun's mass, manage to grow so large so quickly? The universe is currently understood to be roughly 13.8 billion years old, and yet telescopes have detected supermassive black holes already fully formed and feeding voraciously when the universe was less than a billion years old, barely out of its infancy in cosmic terms, still warm from its own creation. Growing a black hole normally takes time. Matter falling toward a black hole does not simply plunge straight in. It spirals inward gradually, forming a hot, glowing disk, releasing radiation as it goes, and that radiation itself pushes back against the infalling material, creating a natural speed limit on how fast a black hole can feed, something astronomers call the Eddington limit. Named after the same Arthur Eddington, whose 1919 eclipse expedition helped confirm Einstein's theory of general relativity in the first place, back when the idea of black holes still sounded to most scientists like a strange mathematical accident rather than a real feature of the sky. Under ordinary assumptions, using that natural feeding limit, there simply should not have been enough time for black holes to grow from stellar remnants up to 1 billion solar masses within the universe's first few 100 million years, a span of time that sounds vast until you try to fit that much patient, careful growth inside it. And yet there they are, sitting quietly in the data, patiently defying the arithmetic, indifferent to how inconvenient their existence is for the equations. Several ideas are being explored to resolve this, none of them fully settled, all of them worth holding gently rather than gripping tightly, the way you might hold a sleeping animal you don't want to wake. Perhaps the earliest black holes were born unusually massive to begin with, collapsing directly from enormous clouds of primordial gas, rather than passing through the intermediate stage of forming a star first, skipping several rungs on the evolutionary ladder entirely, arriving already heavy rather than earning their mass slowly. Perhaps black holes in the crowded, gas-rich environment of the early universe were able to feed faster than the Eddington limit would normally allow, at least for brief bursts, the way a person might, under unusual circumstances, briefly outrun what seems physically comfortable, gasping afterward but having covered more ground than seemed possible. Perhaps mergers between smaller black holes, happening more frequently in the denser, more chaotic early universe, provided shortcuts to bulk that steady accretion alone could not achieve, much like the intermediate mass black holes stacking their way upward through collision after collision. The James Webb Space Telescope, since becoming operational in 2022, has been peering further back into this early era than any instrument before it. Its cold, sensitive instruments catching faint infrared light that has been stretched and reddened by billions of years of cosmic expansion before ever reaching us. It has found galaxies and black holes at these staggering distances in greater numbers than many astronomers had expected, which has been less a tidy confirmation of any single theory and more an invitation to keep questioning the assumptions everyone had been working from, a gentle but persistent nudge back toward humility. And this leads quite naturally into thinking about black holes not as isolated curiosities, but as active participants in the life stories of galaxies themselves. Nearly every large galaxy studied so far, including our own Milky Way, with its own quiet supermassive black hole tucked at the center, appears to harbor one of these giants. And a relationship between the mass of that black hole and the properties of the surrounding galaxy, the number of stars, their velocities, the overall shape of the galactic bulge, follows patterns too consistent to be coincidence. Somehow, these black holes and their host galaxies seem to have grown up together, influencing each other across scales that otherwise seem almost impossibly different. The black hole itself might be smaller than our solar system, while the galaxy around it stretches across 100,000 light years, and yet the two are tied together as though by some slow, patient conversation conducted over billions of years, neither one able to fully explain itself without the other. When a supermassive black hole feeds actively, it can blast out tremendous amounts of energy and radiation, heating and even expelling the surrounding gas that a galaxy would otherwise use to form new stars, effectively regulating its own galactic neighborhood, like a thermostat quietly keeping a house from overheating, even though nobody remembers installing it or setting its temperature. Understanding exactly how this feedback works, how a relatively small object can shape the fate of something so much larger than itself, remains one of the more delicate ongoing threads in modern astrophysics, one that connects directly back to the ancient and modern black holes we've already wandered through tonight, and forward to what still waits, unseen, in the quiet dark beyond. There is another way to think about black holes, one that has nothing to do with galaxies or feeding or the slow architecture of cosmic structure, and everything to do with the strange business of testing our best ideas against the most extreme conditions the universe has to offer. Physicists have spent the better part of a century building two towering frameworks for understanding reality. One is general relativity, Einstein's description of gravity as the curving of space and time, which works beautifully for planets and stars and galaxies, for anything large and relatively gentle. The other is quantum mechanics, the physics of the very small, which works just as beautifully for electrons and photons and the strange, probabilistic behavior of particles, but describes a universe that looks almost nothing like the smooth, continuous space-time of relativity. These two frameworks are each, individually, among the most successful theories human beings have ever produced. Tested over and over in laboratories and observatories and particle accelerators, they have never once been caught making a wrong prediction within their own domains. And yet, when you try to bring them together, when you ask what gravity looks like at the scale of a single particle, the equations do not merely disagree. They break down entirely, spitting out infinities and nonsense where a sensible answer should be. Black holes matter here because they are, as far as anyone can tell, the one place in nature where both theories are forced to speak about the same object at the same time. The outer regions of a black hole, the event horizon, and the swirling disk of infalling matter. These are the territory of general relativity, curved space-time doing exactly what Einstein's equations say it should. But the singularity at the center, that theoretical point of infinite density where all the mass is thought to be crushed down to no size at all. That is where relativity simply stops making sense, and where quantum effects, whatever they turn out to be at such extremes, must surely take over. No one has yet worked out how to reconcile the two, but the effort has not been wasted. It has produced strange and beautiful ideas, string theory, and loop quantum gravity, each imagining space-time itself as something built from more fundamental threads or grains, something not smooth after all if you look closely enough, the way a photograph that seems seamless dissolves into individual dots up close. Neither of these ideas has been confirmed. Both remain, honestly, more mathematical framework than tested physics. But black holes are the reason physicists keep returning to them, keep sharpening the questions, because a black hole is nature's own laboratory for gravity pushed to its absolute limit, a place where the universe seems to be quietly insisting that our two best theories cannot both be the final word. And there is a particular puzzle born from this same tension that has occupied some of the sharpest minds in physics for decades now, sometimes called the information paradox. It goes roughly like this. Quantum mechanics holds, quite firmly, that information about the physical state of anything, a book, a person, a star, cannot simply vanish from the universe. It might get scrambled beyond any hope of practical reconstruction, but in principle, the information persists somewhere, encoded in the details of whatever the system becomes. Yet Stephen Hawking's own calculations, the same ones that predicted black holes slowly radiate away their mass as what's now called Hawking radiation, suggested that when a black hole finally evaporates completely, whatever fell into it over its lifetime is simply gone, its information erased from existence entirely. Those two ideas cannot both be true, not without something giving way. For years this bothered Hawking so much that he made a public wager over it, one he eventually and gracefully conceded he might have lost, and the puzzle itself has since drawn in string theorists and quantum information scientists in roughly equal measure, each bringing tools the others had never quite thought to use. Some now suspect the information isn't lost at all, but rather encoded, impossibly compressed, in a subtle correlations within the radiation the black hole gives off as it evaporates, a bit like a book being burned in the smoke. If you could read every wisp and cinder with perfect precision, somehow still containing every word. It is not resolved, but watching physicists chase, it has been one of the more revealing spectacles in modern science. A reminder that even our grandest theories are still under construction, tested nightly against the darkest objects we know how to imagine. If you have been listening for a while now, drifting somewhere between attention and sleep, you have traveled a long way through this subject without ever leaving the room you're lying in. You started with the simple and rather startling idea that gravity, if concentrated enough, can bend space so sharply that light itself cannot climb back out, the way a valley can become so steep that even the fastest runner cannot escape its floor. You met the event horizon, not a wall or a surface, but a boundary of no return, invisible and yet absolute. You followed the life story of a massive star, burning through its nuclear fuel in stages, iron finally accumulating in its core like ash nobody can burn any further, and then the catastrophic collapse when gravity, no longer opposed, wins in an instant. You sat with the strange, still unresolved question of what waits at the very center, a singularity, mathematics gesturing toward a place physics cannot yet describe. You learned that black holes come in different sizes, stellar ones forged from dying stars, and supermassive ones anchoring the hearts of galaxies, with a puzzling gap in between that astronomers are still working to fill in. You heard how black holes reveal themselves not through what they emit, but through their effects on everything nearby, the stretched light, the orbiting stars, the shadow image for the first time by a network of telescopes spanning the entire planet acting as one. You considered time itself slowing near a black hole's edge, not as a metaphor, but as a measurable fact confirmed by clocks and satellites and careful, patient experiment. You heard the chirp of two black holes spiraling together, a sound translated from ripples in space-time itself, arriving after traveling for over 1 billion years to reach detectors built specifically to listen for it. And most recently, you sat with the deeper tension underneath all of it, the fact that our two best theories of physics still cannot fully agree with each other at a black hole's core, and the possibility that solving this puzzle might change how we understand reality itself. None of that needs to stay urgent in your mind tonight. You don't need to hold on to the equations or the names or even most of the details. What might be worth keeping, if anything, is simply the feeling of scale, the sense that the universe contains objects so extreme they bend the rules we thought were fixed, and that human beings, working patiently over generations, with pencils and chalkboards and telescopes, and eventually entire continents' worth of coordinated instruments, have managed to understand as much about them as we have. That is no small thing. It happened because people kept asking simple questions and refused to stop simply because the first answer felt strange. If you were to step outside right now, into whatever night waits beyond your window, and look up, you likely wouldn't see a single black hole, not directly, not with your own eyes. They are too dark, too far, too subtle for that. But the sky above you would still be full of the stars that might someday become them, ordinary points of light quietly burning through their hydrogen, some of them massive enough that in a few million years, an eye blink in cosmic time, they will finish their story the way we described tonight. And scattered among them, invisibly, are the black holes already formed, some as small as cities, some vast enough to anchor galaxies, all of them shaping the space around themselves in ways too gentle for anyone standing on the ground to feel. There is something quietly comforting in that thought, oddly enough. The universe is unimaginably strange, full of collapsed stars and warped time and the outer edges of what physics can currently explain, and yet here you are, safe and warm, simply resting beneath it, no different tonight than any other night, except perhaps a little more aware of what's actually up there. Let your thoughts settle now, the way starlight settles quietly onto a dark field after traveling for years to arrive. There's nothing more to figure out tonight. Rest well.